Hi students, now I am going to explain the solutions for section 3, single digit answer type questions. First 32nd question. Triphenyl methyl chloride. This on reaction with silver free radical. Dimer plus AgCl formed. In this dimer X, number of aromatic rings present are. Now, because of this silver reaction with this one, you will get this triphenyl methyl free radical. Triphenyl methyl free radical. Now it has to undergo dimerization. There, what is the expectation of the paper setter? You will answer like this. It is the symmetrical dimer. It is the symmetrical dimer. In this, how many aromatic benzene rings are there? 6. But it is not the product. Now see, this triphenyl methyl free radical, it is not planar. If it is planar, in between these rings, crowding will be there. To minimize the crowding, it exhibits propellar shape. In that propellar shape, this carbon free radical and directly attached carbons in the ring, these 4 only in the same plane. But this benzene ring not in the same plane, it is in another plane. In the same style, not only the triphenyl methyl free radical, triphenyl methyl carbocation, triphenyl methyl carbanion. These also have non-planar structure, propellar shape. Propellar shape. Now, if it undergoes this type of symmetrical dimerization, crowding will increase. So that's why what happens. One of its resonance structure. See, this carbon free radical, individually it is in resonance with this, individually it is in resonance with this. Individually resonance is there. From this, you will get this resonance structure. Now, this free radical and second free radical, triphenyl methyl free radical, these two will combine with each other. This one is this one is this. So it is the unsymmetrical dimer formed, not the symmetrical dimer. Unsymmetrical dimer formed. In this, how many rings are there? Aromatic benzene rings, 5 are there. So now what is the answer? 5. See, actually, from this experimental observation only, we came to conclusion that this triphenyl methyl free radical is non-planar, has non-planar structure, propellar shape. So answer is 5, but not 6. Next question, 33rd question. How many resonating structures are possible for the compound? 2 naphthalenes are attached together. For this, how many are possible resonating structures? See, for naphthalene, how many resonating structures are possible? 3 only possible. See, in this ring, 3 double bonds, 2 possibilities. In this ring, 3 double bonds, 2 possibilities, like that. Overall, 3 resonating structures are possible. You may get one doubt, sir, shall we write like this? Shall we write like this? For this plus minus, like this, if we write so many, you will get na. But see, it is the most energetic structure. Its contribution to the resonance hybrid structure is very, very less. So almost we should not consider it as a resonating structure. We should not consider as a resonating structure. Why? Because energy should not be very high when compared with the resonance hybrid structure. So that's why for aromatic compounds, this type of structures we don't include as resonating structures. Why? Because for this energy more. So we don't include them. So now for this naphthalene, 3 are possible. No? It is naphthalene, it is also naphthalene. So by keeping for this one, this structure, here 3 possibilities. 3. Next, in this naphthalene, by keeping this one, here these 3 possibilities. 3. In this naphthalene, By keeping this structure, here these three possibilities, three. So 3 is 9 resonating structures are possible for this. 3 into 3. 9 resonating structures are possible for this. Now let me write the next questions. How many of the following ions have at least one structure in which all atoms will have their complete octet except hydrogen? In which of the following ions in their resonance structures, at least in one resonance structures, all the atoms to be satisfied octet except hydrogen? In how many molecules? Now how to answer this one? To the carbocation C plus, if we interact with the lone pair like nitrogen, oxygen, fluorine attached, then that one is more stable. Why? Because in one of their resonance structures, all atoms satisfy octet rule. Next, to this C plus, such a type of heteroatoms may not attach directly. If they are in conjugation also, then okay. In one of their resonance structures, all atoms satisfy octet rule. Based on that logic, now we have to answer. Now see, to this C plus, oxygen is attached directly. Now in its resonance structure, what happens? What is its resonance structure? This is the resonance structure. See, now all atoms satisfied octet rule. This oxygen, 3 covalent bonds, 6 bonding electrons, 3 to 6, plus lone pair, 8 electrons. Now all atoms satisfied octet rule. Now you may get one doubt, sir, is it stable? At oxygen, positive charge is there now. Oxygen more electronegative. See, if it satisfies octet rule, then for that point, no problem. It satisfied octet rule, na? So that point will not play major role. Now it is stable only. So in one of its resonance structure, all atoms satisfied octet rule. Next. Now, for this also, C to the C plus nitrogen attached directly. So that's why in one of its resonance structure, all atoms will satisfy octet rule. See here, oxygen not attached directly, but to this C plus it is in conjugation. This lone pair will convert into pi bond. This pi bond will be shifted to here. Now positive charge will be at this oxygen. Now all atoms will satisfy octet rule. So this one correct only. Next, now to this C plus, nitrogen not attached directly and it is not in conjugation also. See, lone pair, single bond, double bond. This side conjugation is there. This side conjugation is not there. So that's why with the lone pair at nitrogen and C plus, no conjugation, no resonance effect. Now this one. Now for this one also possible, like this resonance structure. See, commonly we can say acyl carbocations. It is benzoyl carbocation. Benzoyl carbocation. In one of their resonance structures, all atoms satisfy octet rule. All atoms satisfy octet rule. So that's why we can say it is more stable than the tertiary butyl carbocation also. More stable than the tertiary butyl. So like this, like that structure possible. So here also in one of its resonance structure, all atoms satisfying octet rule. Now here you will do mistake. So here lone pair is there, conjugation is there. See, now this nitrogen, sp2 nitrogen, this lone pair is in molecular plane. This empty 2p orbital is in the plane perpendicular to the molecular plane. In all these examples, to this empty 2p orbital, these are all parallel. To this empty 2p orbital, these lone pairs are parallel, so lateral overlapping or delocalization possible. But here it is empty 2p orbital is in this way, lone pair is in this way. So with this delocalization not possible at all. Delocalization not possible. So it is not the correct answer. Next to here also. See, here delocalization possible. Like this delocalization possible. So now here in one of its resonance structure, all atoms at space octet. This one also correct. This one same style. This lone pair is in sp2 hybrid orbital, sp2 hybrid orbital. So it is not in conjugation with this. So for this not correct. Now here this lone pair not in conjugation with this. So this one also not correct. So now what is the answer? A, B, C, E and G. So total in 5 compounds, in one of their resonance structures, all atoms satisfied octet. So answer is 5. Now come to the next question. How many of the following species are aromatic in nature? What is the Huckel's rule? Planar monocyclic compounds with 4n plus 2 pi electrons are aromatic. Anti-aromatic, planar monocyclic compounds with 4n pi electrons are anti-aromatic. So as per that statement, we have to decide this one as per the Huckel's rule. It is 18 inulin. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 carbons, monocyclic conjugated polyene, 18 inulin. Now, here in this case, in between these hydrogens, crowding is not so high. Now, that's why it is planar, 18 inulin. That's why all 18 inulins are aromatic. So it is aromatic. You can consider benzene as 6 inulin. Next, remaining anilines, some are planar, some are not non-planar. So some of their isomers only planar. So by looking that example only, we have to conclude. But all 18 anilines are aromatic. Now, cyclopropenyl carbocation. On a planar, 2 pi electrons are delocalized. So it is aromatic. Now this one, 4 pi electrons are delocalized. 4 and n value 1. So it is anti-aromatic, not aromatic. Next, this one. Here, these are sp2 carbons. So that's why delocalization possible for 2 pi electrons. So that's why cyclo tetraenyl dication. This one also aromatic. Next, this one. Cyclopentadienyl anion. 4 plus this 2. 6 electrons are delocalized. Now, this lone pair is in the molecular, in the plane perpendicular to the molecular plane. That is in 2p orbital. So, delocalization possible. So, this one also aromatic. Now, here it is boron. It is just like C plus. Now, here empty 2p orbital is there. Empty 2p orbital. That is in the plane perpendicular to the molecular plane. 4 pi electrons. 4 and pi electrons delocalization. So, it is anti-aromatic. Now this one 6 pi electrons delocalization is not there. So it is not aromatic. Next, this one, it is sp3 carbon. So here conjugation continuity is there and it is non-planar. So that's why it is not aromatic. It is non-aromatic. Now these two rings individually 6 pi electrons delocalization is there. So that's why this one aromatic. Now benzene, see in this triple bond, 1 pi bond formed by 2p orbital overlapping. This is p pi pi. What is the specialty of this one? Only in this molecule. Pi bond is possible with hybrid orbitals. In this way, sp2 hybrid orbitals are overlapping. It is pi sp2 sp2. This pi sp2 pi bond is in the molecular plane. Remaining are in the perpendicular planes. So this 3 pi bonds delocalization only possible. This one delocalization not possible. So that's why 6 pi electrons delocalization. That's why benzene is also aromatic. In this benzene, all the carbons are sp2 only, not the sp. So now how many are aromatic? 1, 2, 2, 3, 4, 4, 5, 6. So answer is 6. 6 compounds are aromatic. Now come to the next question. Among the following, how many can give effervescence with sodium bicarbonate? Here, what is the logic? Any acid-base reactions are favorable in the direction of formation of the weak acid, weak base. Based on that logic, now what conclusion we can give? Acids which are more acidic than H2CO3 carbonic acid. Only such acids can decompose sodium bicarbonate and gives effervescence CO2 gas. Now, for carbonic acid H2CO3, pKa1 value 7.1. Now, acids with their pKa value less than 7.1, such acids are more acidic than H2CO3 and can decompose sodium bicarbonate and gives effervescence. Based on that logic, now we have to decide. See, phenol. Phenol more acidic than water alcohol, but still less acidic than carbonic acid only. This phenol. Next to ethyl alcohol. These two are less acidic than carbonic acid H2CO3. So these cannot give effervescence. In this phenol, if you substitute electron withdrawing groups NO2, now one NO2, now it is still less acidic only. 2,4-dinitrophenol, 2,4,6-trinitrophenol, that is picric acid. These two are more acidic than H2CO3 and can give effervescence with sodium bicarbonate. So picric acid is correct. Next, now carboxylic acids are more acidic than carbonic acid H2CO3. Carboxylic acids, acetic acid, benzoic acid. So carboxylic acids can give effervescence with sodium bicarbonate. Sulfonic acids also more acidic than H2CO3. Now come to this one. This type of compounds, a sequence is there. Here it is a deltic acid. If four are there like this, that is called square. It is square now. So that's why that is called squaric acid. Next 5-member ring, croconic acid. Next 6-member ring, rongenoic acid. What is the specialty of all these? When these loses proton, their conjugate bases stabilized by identical resonance structures. In this case, for all these, their conjugate bases stabilized by identical resonance structures. That's why these are more acidic, and these are more acidic than this one and this one. More acidic than H2CO3 carboxylic acid. So that's why these two can give effervescence with sodium bicarbonate. This squaric acid not given. If they give, this one also correct. This type of structure with the 6-member ring, that one also can give effervescence with sodium bicarbonate. But this one not given in the options. Now how to decide this one? It is the conjugate acid of aniline. It is the conjugate acid of methylamine. Aniline aromatic amines are less basic than the aliphatic amines. For this pKb value 9.41, for this 3.31. Strength of the base is inversely proportional to pKb. So aniline is less basic than methylamine. Now if base is weak, its conjugate acid is strong. For a conjugate acid-base pair at 25 degrees centigrade, pKa plus pKb equal to pKw 14. Aniline pKb value 9.4. Now aniline ion pKa value 14 minus 9.4, 4.6. This pKa value less than the pKa of H2CO3, 7.1. So aniline ion more acidic than H2CO3 and can give effervescence with sodium bicarbonate. Next, methylamine pKb value 3.3. Now methyl ammonium ion pKa value 14 minus 3.3, 11.2, 10.7. Now this pKa value more than 7.1. So methyl ammonium ion less acidic than carbonic acid. So it cannot give effervescence with the sodium bicarbonate. vitamin C. At present, everybody using this vitamin C tablets. It is also available in the citrus fruits. It will improve the immune system. Now in this vitamin C also, this hydrogen is more acidic. Why? If it loses proton H plus, now its conjugate base stabilized by resonance with C double bond O. See, to the C minus also, if electrons with the drawing group like C double bond or C triple bond N is attached, stability will increase now. So because of that reason, among these four again, this one is more acidic. And finally, vitamin C more acidic than H2CO3. Vitamin C pKa value 4.7. So it is nearly as acidic as acetic acid. So this one also more acidic than H2CO3. So that's why it also can give effervescence. Now how many are giving? C, D, F. So answer is 6. 1, 2, 3, 4, 5, 6. So these are the solutions for PTA2 chemistry paper. Okay, thank you students.